Smart data. It is the real-time data from multiple sources, from the web, from IoT sensors, and most recent application data. Our analyzer uses the smart data, performs analysis, and provides critical information to protect environment, health, and safety of the community. Ozone data. Ozone in the stratosphere is good for the planet, while in the Earth's atmosphere it's harmful for living beings. Here are some of the harmful effects of the ozone in atmosphere that is listed. The presence of ozone is available in the air, which is read and monitored by airnow.gov, or it can be created by industrial processes. When temperatures elevating above prescribed levels, VOCs can react with nitrogen oxides to generate ozone. The goal is to protect the environment and the workforce by monitoring, alerting, and responding. This is a chart of AQI. Any ozone levels of AQI above 100 is not good. The data sources for this analyzer is the real-time data from our local geographic location and the real-time data from IoT sensors, along with the characteristics of the VOCs in work zones like flash point and auto ignition point. In our first process, to monitor air quality alert, you are looking for this condition where AQI is greater than 100 and if the temperature hits the T1, the threshold value. It automatically switches on the exhaust fans to provide additional cooling, sends notification to the system, and send text messages. For our second use case, we are looking for the volatile organic chemicals characteristics with regards to flash point and auto ignition temperature. The goal is to prevent fire accidents, and the algorithm is it's monitoring for the T2 threshold temperature, and if it hits, it will send text notification or calls users. The system configuration is the IoT devices are wirelessly sending data from sensors, and it can also be used to control devices. We are using a Raspberry Pi and a sensor to get the data. We get the AQI from the EPA, and cell phone messages and phone calls are pushed to the users. Now we are going to see the live demo. For our demo, we are going to show two different locations that can be geographically far apart. This is the chemical storage area and usage work zone. The other one on the far right of the room represents the computer system and the users operating the system. Within the storage area, volatile organic chemicals are stored in special flammable lockers. We have placed our IoT sensor close to the VOC storage location and VOC workplace. Our system reads air quality index data that reflects ozone levels in the air from EPA's data center. This data is available on their website, airnow.gov also. We want to show that the current AQI value from the website is read live into the application. On the airnow.gov webpage, we look for Utah, and when you select, you see the results for Salt Lake City, and that is displayed as AQI value of 35. Going into our application, you would see that the value is read through a web service and displayed on the HMMS screen. The next data is the temperature coming in from the VOC work zone. The IoT unit is placed near the work zone, comprising of a single board computer, which is a Raspberry Pi board, connected to a sensor to send temperature and humidity to the system. The sensor reads to an accuracy level of 1/100th of a degree Fahrenheit and will wirelessly transmit to the system. Giri is our site safety personnel who will receive text messages from the system when the temperature reaches the first threshold value. His cell phone number is configured to receive the message. In our first demonstration, we are going to increase the temperature to the first threshold value, which is set to 76 degrees Fahrenheit, and he's going to do that by placing a hot water glass next to the sensor. Once the temperature reaches the threshold value, the color of the display of the HMMS application will change to red to alert the system user. At the same time, we should see an alert sent as a text message on Giri's phone. The LED light will also turn on, which is a signal received from the system to turn on the cooling fans. Now you would see the temperature is increasing on the application on the right hand side. It is getting closer to 76. You're almost close to 76 now. Now it is over 76, and you see the color change to red. And also the LED light on the IoT device is flashing. We also see that the text message is received. Now we saw that it's operating. Now we are trying to bring the temperature down by placing an ice cube glass, and the cooling fan should automatically turn off once the temperature goes below 76. You see the temperature is now reducing. Now it reached 76 and below, and the lights turned off and the signal also changed. That concludes the first use case. For a second use case, we are going to increase the temperature further to the next threshold value, which is 78 degrees Fahrenheit, that's what it said. Sandeep is our emergency responder who will receive an automated phone call when the temperature rises to this critical level in the site. He's going to place the hot water glass again to increase the temperature further. The temperature is already at 76.28 now. Once it reaches the second threshold of 78 degrees Fahrenheit, we should be getting an alert on the screen, as well as an automatic phone call will be placed to the emergency responder. Sandeep is holding out his phone to show that once it reaches that number, a phone call will automatically be placed, and an automatic message can also be played as when the phone call is taken. For our demo, we are just showing a phone call being initiated automatically from the system. We are almost close to the second threshold, 78, 77.54. We just hit the second threshold, and you see that light is flashing on the IoT and also on the screen. And we are waiting for the phone call to come, and there it is. The phone call just comes up automatically, and when the user attends, he will get the automatic message. That concludes our demo here.